So the first group was cylinders. And what makes them unique is that there's a variable missing. Our next group are called quadric surfaces. And what makes them unique is they have squares. They always have squares. There is one equation here where one variable is not squared. All of their equations, all of their variables, everything's going to be squared. And as we go through this, I'm also going to talk to you about traces. Because being able to look at this equation and tell that it's an ellipsoid requires you to be able to identify the traces. So we need to talk about what exactly a trace is and how we find a trace. So the formula for an ellipsoid is x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Looks very similar to the ellipse we just did in the last problem, except it's got all three of them in there. So what we're going to do to help us identify these solids is we're going to use traces to identify the two-dimensional cross sections, and then we're going to piece them back together to create the solid. The easiest way to do a trace is to just let one of your variables equal 0. There are some cases where you can't do that, and we will come across that today, and I'll show you why and what we would do in those cases. But the easiest way to do it is just let one of your variables equal 0. If I want to know what the cross section for this surface looks like in the xy plane, then just let z equal 0. In the xy plane, z equals 0. So in general, a trace is a cross section of a three-dimensional surface, and it's found by letting one of the variables just be equal to a constant. If you think of a box, it's got a length, a height, and a width that could all three be different, technically. So all our surfaces are going to have three different cross sections. The easiest constant to let them be equal to is just 0. But there are a few cases where we can't let it be equal to 0. And we'll come across those and see what to do when that happens. So for our ellipsoid, we want to know what the traces are. I want to know what the individual pieces are that come together to make up this surface. So for my xy trace, I'm going to let z equal 0. And most of the time when we let a variable equal 0, it just wipes that out of the equation. So if I let z equal 0, we're left with a two-variable equation. We're just left with a two-dimensional curve. We're left with x squared over a squared plus y squared over b squared equals 1. And what is that? If we were to graph that, what would it create? An ellipse. If a and b were not the same, it would create an ellipse. So when we slice this thing and we look and see what it looks like in the xy plane, it looks like an ellipse. If we look at the YZ trace, and we do that by letting x equal 0, that's just going to wipe the x out of the equation. And that's going to leave us with y squared over b squared plus z squared over c squared equals 1. And it's another ellipse. And then there's one more trace we can check, xz trace. And what do we do to find our xz trace? We're going to set y equal to 0. And what sort of curve will that create? An ellipse. So no matter how we slice this thing, we're always getting ellipses. So the xy plane is the flat horizontal plane that's parallel to the floor. That is an ellipse. So pretend that's flat. And we're looking down on that. I'm going to label these and do them in different colors. The YZ trace, it stands vertical and we're facing it like it's the board. That is also an ellipse. The XZ trace also stands vertical, but it's turned 90 degrees from the YZ trace. So this one looks more like a sphere. But depending on the ABC values, any of these points can be stretched out to make this shorter and fatter or taller and skinnier. More like an egg shape or a football shape or something like that. But no matter which direction we slice this thing in, we're getting an ellipse every time. So knowing those basic two-dimensional objects can be very helpful in deciding on what the three-dimensional surface is going to be. And when all of your traces are ellipse, they come together to make an ellipsoid. Very similar to a sphere. With a sphere, we're going the same exact distance from the center in all directions. There's one radius that works in every direction. With an ellipse, it's not perfectly equal in every direction. We've got those different radii out in those different directions. I want you guys to try this one. I want you to try to figure out the traces and what it's going to look like. And I've got it up where the z is not squared here, but we could easily turn this around and say x equals z squared over c squared plus y squared over b squared, or y equals x squared over a squared plus z squared over c squared. And that's just going to change the orientation of the graph. Yes, if you set z equal to 0, you might have a problem. That's one of the cases where you might want to think of z equal to a constant. So the only time a sum of squares is equal to 0 is at the point 0, 0. So you could set z equal to a constant as well, and you could do any constant you want to. What do we usually see x squared over a squared plus y squared over b squared equal to? And equal to 1, and it's an ellipse, right? So if it's more convenient and it's more helpful, and it's more easily recognizable, you can set it equal to some other constant. And this is one of those cases where equaling 0 doesn't really make a whole lot of sense, but equaling 1, and voila, we've got an ellipse. Okay? So our xy trace is an ellipse. And I don't get that by plugging in z equals 0. I get that by plugging in z equals 1. Because the rule for a trace is not plug in 0, it's plug in a constant. It's a cross section. Z equals 0 is just a really convenient one usually, but it's not the rule. Now for our other two traces, I would use 0. If we let x equals 0 to find the yz trace, what two-dimensional equation are we left with? No, we're going to let y squared over b squared. The b is just a number, so don't let that mess you up. If I have a single linear variable is equal to a squared variable, think back to what we would do in algebra class with that kind of equation. What would that graph look like? If it was just y's and x's, what would it look like? It would be a parabola. If one was linear and the other was quadratic, it would be a parabola. So this is a parabola. We need to know what direction it opens in. So again, think back to algebra class. Y equals x squared opens in what direction? It opens in the positive y direction. So parabolas open in the direction of their linear variable. So in z equals y squared over b squared, it's going to open in the positive z direction. The b squared is just a number. It's just going to adjust how widely or narrowly the parabola opens. All right, xz trace, if we let y equals 0, we've got z equals x squared over a squared. One of them is linear, one of them is quadratic. What's the shape? Parabola. What direction is going to open it in? Positive z. So we've got another parabola opening in positive z. I know what the cross sections of this surface look like in all three directions. And we're going to try to put them all back together to create a surface. I haven't told you what the name of this is yet because that would give away what the traces are. Usually those cross sections, whatever those two-dimensional cross sections are, help us to name the object. So if I told you what the name of it was, you would have known what the cross sections were. I'm going to draw my parabolas first. So my YZ trace, that is what we're facing on the board. We've got a parabola opening in the positive z direction. The XZ trace is also a vertically oriented plane like the YZ plane, except it's turned 90 degrees. And in that plane, which cuts into the board, we have another parabola opening in the positive Z direction. So that one's like starting out at us and cutting into the board. Now remember, we said when Z is 0, it's just a single point, 0, 0. But as we slice this thing at larger values of Z, constants of Z, we see ellipses. So the XY trace is an ellipse. So as we slice this thing horizontal, we see an ellipse. So we saw two different types of traces. What were they? Ellipse and parabola. We had to come up with a crazy name that puts them together. It's not a cylinder because we didn't have one shape get repeated forever. Yes, elliptic paraboloid. The traces, most of the time you can just do 0. If for some reason 0 is not making sense or you're not recognizing what sort of graph it makes with 0, you might have to use a different number. Usually 1, because a lot of these other equations, they have 1, equal to 1 in the conic sections. All right, I'm going to give you the names though this time, because these next two their names are really weird. And you're going to wonder why in the world they named them this, but once we see the picture, you'll see why. In this one, we actually have something this shape close by here. This next one is called a hyperboloid of one sheet. Hyperboloid means it's made of hyperbolas. A hyperbola, it's kind of like a parabola, except there's two of them and they face away from each other. They don't touch. The equation for a hyperbola looks exactly like an ellipse, but the plus is replaced with a minus. So you can recognize the equation for a hyperbola. Look for an ellipse, but with subtraction. So we'll see it in this one. All right, for a hyperboloid of one sheet, the equation, or one possibility for the equation, if we move around where this subtraction is, it will just change the orientation of the graph, which direction it's opening in. So we'll get a little review of hyperbolas as we do this. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. XY trace, let z equal 0. We've got an ellipse. YZ trace, you're going to let x equal 0. It's a hyperbola. It's the format for an ellipse, but the addition got changed to subtraction. It's a hyperbola. And one thing that we have to add to our description is what direction it opens. That's also extremely important. Hyperbolas open in the direction of the positive variable. The one that is positive in front is the direction that these hyperbolas open in. Okay? So these hyperbolas are going to open in the positive and negative y direction. Hyperbolas always come in pairs. There's two of them, and they open away from each other. So they open in the positive and negative y direction, because the y is the positive variable in this equation. The z has the negative in front of it. They always open in the direction of the positive variable. The xz trace is x squared over a squared minus z squared over c squared equals 1, which is again a hyperbola. The positive variable is the x. That means it opens in the positive and negative x direction. I'm going to do the ellipses last, because the ellipses are what's going to connect all of our hyperbolas together. So we've got a set of hyperbolas in the YZ plane. The YZ plane is the board that open in the positive, negative y direction. So they kind of just look like parabolas, facing away from each other. I'm actually going to pull them in closer to each other. We don't really know where they are right now because we don't know any other values. There is also a set of hyperbolas in the XZ plane opening in the positive and negative x direction. So that's like forwards and backwards. So back here and up here. Tree trunk. A tree trunk is a very good guess. Now there are ellipses in the XY plane that connect all of these. Sharon Harris. It might be better to draw it off of the XY plane and then insert, or XYZ, and then insert the XYZ later. I have found that I draw it much nicer That's still not great, but it's way better than the one above it. This is a hyperboloid of one sheet because when we put this all together, it made one solid object. The next one is called a hyperboloid of two sheets. It could be written with them in any order. I could have the X in the front, I can have the Y in the front. It would just change the direction that the stuff is pointing in. I could have X minus Y minus Z, I could have Y minus Z minus X. The traces would not change, but it would change the direction that things are pointing in. It would still be a hyperboloid of two sheets. The traces would still be the same, but we would just say like opening in a different direction. The XY trace here is tricky. If we let Z equal 0, I've got negative x squared minus y squared equals positive 1. Mathematically, that doesn't even make sense. But if we let z equal a constant, we would make it equal to 2. We would subtract it over, and then it would be negative 1. And then we would multiply everything by a negative 1. So I would make sure actually that z squared over c squared equals 2. I would make z squared over c squared equals 2. And then I would do some manipulating of this equation and have x squared over a squared plus y squared over b squared equals 1. So the z equals 0 here is not even possible because you have a negative equal a positive, which is not going to happen. As we move up and down the z-axis, I did. What's the xy trace? All right, gotta do this quick. What's the xy trace? X squared over a squared plus y squared over b squared equals 1. It's an ellipse.
Oh, b squared, my bad.
Just because we've got different, a and b might be different. So it's an ellipse. All right, yz trace. We've got z squared over c squared minus y squared over b squared equals 1. That is a hyperbola because it's a difference of squares. What direction does it open in? It opens in the direction of the positive variable. We're going to have hyperbolas opening in positive and negative z direction. Xz trace is z squared over c squared minus x squared over a squared. Is another set of hyperbolas. Again, opening in the positive and negative z direction. This looks exactly like the last one. There's one tiny difference. What's the difference in this? There's one difference in the traces. If you have notes on the last one. In the last one, our hyperbolas opened in different directions. One set of hyperbolas opened in the y direction, the other set of hyperbolas opened in the x direction. In this one, both set of hyperbolas open in the same direction. We're going to have two bowls. So in the YZ plane, which is the plane that we're looking at flat on the board, we've got a set of hyperbolas opening in the z direction, the positive and negative z direction. In the XZ plane, which slices perpendicularly into the board, we also have a set of hyperbolas opening in the positive z direction. And now these two bowls still are not connected, but the arms of these bowls are connected with ellipses. So we see this is called a hyperbola of two sheets because our traces are again ellipses and hyperbolas, but because those hyperbolas, both of those set of hyperbolas are opening in the z direction, they don't end up connecting and we end up with two completely separate surfaces. So it's a hyperbola in a hyperboloid in two sheets. And again, we can change around in this equation which variable comes in the front and which one come behind the minuses, and that's just going to change the orientation of this graph. So we've got z as the positive variable, and this graph opens in the z direction. Our bowls are pointing up in the positive z and down in the negative z. So if we put x in the front, they would open in the positive and negative x direction. If we put y in the front, they would open in the positive and negative y direction.